This video is going to look at how we use sigma notation to represent Riemann sums, or how to kind of show what they total up to. So Riemann sums are the standard way to calculate the area under the curve. And this is going to be equal to the sum from I equals 1 to n of f of xi times delta xi. And let me label this a few places. So this is how many rectangles you want. So how many rectangles are you slicing it up into? This is some x value within the slice, and this is the width of the slice. And f of x is the height of the slice. So I'm using this language of slice because it'll connect with something we do later. If you prefer rectangle, that's fine. So we're slicing it up into a bunch of rectangles, n rectangles, and then we pick a point within that interval. We've talked about them before. It can be the left-hand value, it can be the right-hand value, the value that produces the highest thing. It can be the midpoint, it can be an average, etc., etc. And then by plugging it into the function, that produces a height from an x value. And then the delta x is just the width of that slice. And so the more rectangles that are used, the better the approximation. And f of xi can be the value at any point. Let me double check what I had here. Any point within the interval. And with infinite partitions, or infinite rectangles, so if you take the infinite sum, the sum will be exactly equal to the area under the curve. In other words, if we have the infinite sum, we get the exact area. So whereas before, we have the area is approximately equal to this value, now we can say the area is exactly equal to the sum from n equals 1 to infinity of f of xi times delta x I, which I'm also going to write using this notation here, the sum of n equals 1 to infinity of f of xi times dx. dx is what we call a differential, and it's an infinitely small interval of x. So if you get to the smallest delta x that you can without being 0, that is a differential. So now that leads us into a concept of the integral. Definite integrals calculate the accumulation of change of a rate function over a specified domain. We write this like so. The integral from a to b of f of x dx, and that's defined as being equal to the infinite sum of I equals 1 to n f of xi times dx. So in other words, what we had just defined before, and these are the bounds, a and b. So that's just, what number you start with, what number you end with. So the definite integral can be calculated using a Riemann sum, using the infinite Riemann sum. That shouldn't be n, that should be infinity. Oops. If the antiderivative is known for a function, we'll talk about antiderivatives later, that function can be integrated. And this result is known as an indefinite integral. So just like with derivatives, where we said that sometimes you can get a specific situation, like the derivative at a specific point and get an exact value, that's like our definite integrals. We've also talked about how you can have an indefinite integral, which is the kind of general form of going to any point on the function. So integrals are just ways to calculate the accumulation of change, or on a graph, the area under that curve. And they're defined using this idea of a Riemann sum for a definite integral. For an indefinite integral, they'll be defined using the antiderivatives that we'll talk about in another video.